we know that when we have a symmetry, continuous symmetry, we should be looking at solutions. And we know that continuous symmetry implies that we should have so-called relative equilibria and relative periodic orbits. Now, relative equilibria in this subject are always called traveling wave, because if you stare at a flame front, you'll just see it spiraling at a constant velocity. So you'll see it just moving. They'll be looking like a traveling wave. Yeah, some pictures like waves. Now, relative periodic orbits are very hard to see by naked eye because you look at the flame, it does all kinds of stuff, and then 76.34554 seconds later, it's actually the same flame, but it's been turned by some irrational angle. That's a relative periodic solution. But because we are studying group ON and not SON, there are additional solutions which are important. So let me just say what they are. O2 has reflection, which means that there is a solution that looks like that. I start with my state, U, I start at X, and I add to it some shift, very precise shift, and I look at it very precise time P later, and to be totally devious, I also apply a reflection to this. So I take this, I look at it, and then later I reflect the solution. And what do you know? I get the same thing at X at time 0. So that's a new solution we haven't seen when we started just SON, which was relative periodic 1. This one uses also an extra group element, which is reflection. And I might have made an error someplace. So now, this one is something we're not used to, because if I go time twice the time, well, that means if I apply reflection 2 times. So I do it and reflect it again. If I do it for that time, then it'll turn out to be periodic. So Ux0 will be U of X 0, exactly periodic, 2 times the prime period. So it's pretty periodic. So we are used to that kind of thing because when we had discrete symmetries, we knew that if we divided pi in 2 pieces and we went twice as long, the prime periodic orbit completed the cycle and became a full periodic orbit in a state space. So we're used to this. But it's a little bit weird. You have to wrap your head around it because its prime period requires some kind of shift. And this shift disappears once you repeat it twice, because first you went this way and then you went that way and you just come where you started. And I still insist that you should do all your calculations in a fundamental domain with these shifts, etc. Now, when you think of it a little bit more, it'll be even more painful because you realize that whenever you have a relative periodic orbit, you're not looking at periodic orbit, you're looking at a torus. That's the real object. And now it says when you have group O2, there are 2 kinds of tori. So there's some subspace, which I showed you was a huge dimensional subspace. Thing I called U+. It was an invariant subspace. And now there are 2 kinds of solutions. There are relative periodic orbits and equilibria, etc., and they have a property, they're tori, that you find one torus like that, and that's called a relative prime periodic orbit. I'll put a tilde on it. That means that there is its copy as well under reflection. When you apply reflection, if this guy is going that way, the other guy is going the opposite way. So if you're on a flame front, you're moving this way, there's always solution going the other way. And then there are these guys, which I just can't visualize myself, they're self-dual. So that's a torus. I don't know how to draw it. It's a torus. We knew how to do this when we were looking at pizza and just periodic orbits. There are periodic orbits which appeared in pairs and periodic orbits that went this way, repeated itself, came back. So they're self-dual under reflection. And now we have tori, and there are two kinds. The guys going this way, guys going that way, and they're self-dual ones. And this we call pre-periodic because under doubling the time they repeat themselves exactly, and these ones we call periodic, relative periodic. So the shortest cycle of 3-disc pinball is of that kind. I go there and I just repeat my motion. So it looks like that. Or there are things that I go visit 3-disc and I can go right, or I can go left. So yeah, I can. And now that's just the beginning of the story, because now when we have the dihedral group, so when you look at solutions which are Dn subgroups of SO2, then, you know, these guys are divided in little pieces, and this happens and that happens, there are more of them, and da-da-da. And it turns out, even very simple cases, it's not very easy to enumerate all invariant orbits, but you have to do it because it's immensely important when you try to organize the world of all solutions. You know, you really have to classify them by their symmetries. We know this because our zeta functions require that they're classified by their symmetries. That's how they went into the calculations. And they also help us organize the state space.